The Nile River is ancient, powerful, and unpredictable. For millennia, people have tried to measure and tame it, but the river kept breaking the rules. That is, until the 20th century, when a physicist and mathematician, Harold Hirst, discovered a hidden pattern that gave Egypt control over its water. His discovery revolutionized how we understand the world. We're going to explore the maths behind rivers, long-term memory, and how it led to the discovery of fractals. Egypt and the Nile River have a long history. The flooding of the Nile River is a regular occurrence, and this flooding brings fertile soil that have supported agriculture for thousands of years. But this flooding is irregular. Some years, the river brought too much water, damaging infrastructure and crops. In other years, too little water brought famine. Fast forward to the turn of the 20th century, agriculture in Egypt had exploded, particularly in cotton, a highly water-intensive crop. Population was also growing. Industry was expanding. Between 1882 and 1907, the population had almost doubled, from 6.7 million to over 11 million in just 3 decades. The country needed something the Nile could not guarantee: dependable water and reliable electricity. A dam promised to offer both. In 1902, the first Aswan Dam was completed, at the time the largest brick structure of its kind. It was raised twice in the following decades, each time trying to keep pace with increasing demand. But there was a problem. The dam wasn't just struggling with demand from farmers, it was struggling to handle the behaviour of the river itself. The first decades of the 1900s brought unpredictable flows with far more water than engineers had predicted. Therefore, only 5 years after it was opened, in 1907, they had to raise the walls by 5 metres, and then again in 1920 by 9 metres. This was a problem. The reservoir couldn't protect against floods because it was already full. They had to let floodwater through that could instead have been stored and used to keep the flow of water more steady. By the mid-20th century, it was clear that Egypt would need an entirely new dam, one that would be capable of handling an exponential increase in population and to store water for decades. The question was, how large would the new dam need to be? The Egyptian government tasked its specialised department, headed by Harold Edwin Hirst, with a mission to determine how much storage a new dam would need to regulate the Nile's flow and to protect Egypt against extreme droughts. At first glance, this problem might seem straightforward. Measure how much water the Nile carries each year, calculate the average, and design a reservoir large enough to buffer the difference. But as we saw, the flow of the river in a given year is far from the average flow, and defied expectations by assuming random fluctuations around the mean. And in a simple world, river flow would be constant. If supply always equaled demand, no reservoir would be needed at all. A reservoir, in essence, tries to manufacture this easier-to-manage scenario. It stores excess water during wet years and releases it during dry ones, smoothing out nature's extremes. But this only works if the reservoir is large enough. So how large is large enough? Hirst realised that he needed to look at the river in a different way, and believed that data on which previous dam designs had been built was insufficient. Therefore, he collected relevant data over a much longer period of time. Luckily, he had help, because the Nile River has some of the oldest river readings in the world. Peak river levels were meticulously recorded by the Arab settlers at Rhoda each year from the 7th to 13th centuries. What he found was unexpected. Instead of fluctuating randomly around the average, the river showed long-term memory effects. Wet years tended to cluster together, like the river remembered the levels it had in previous years. Dry years did the same. It led to him describing the effect as a long-term memory effect, where self-similar patterns appeared in the data. This meant that droughts could last for far longer than anyone had assumed. The implication was profound. the storage required to reliably relegate the Nile was far larger than traditional engineering methods predicted. Decades later, these insights would help shape the construction of the Aswan High Dam in the 1960s. When completed in 1970, it created Lake Nasser, one of the largest artificial reservoirs in the world. The dam brought electricity, flood protection, and reliable irrigation, but it also introduced new challenges: sediment loss, ecological disruption, and geopolitical tension with upstream nations. It is incredible to consider the amount of work and ingenuity Hearst invested into rescaled range analysis and long-term memory effects. In the time before computers and the internet, the manual labour required to compute thousands of years of potential river flows, gather paper records from libraries around the world, and meticulously transcribe them took years to get any results. But what is incredible is that Hearst had the ingenuity to ask the question, is the Nile unique, or just one example of a system exhibiting long-term memory effects? He therefore did all this work again, looking at records for European and American rivers, the width of tree rings, depth of lake sediment layers, and annual temperature and pressure readings. He found that many of these time series, when looked over hundreds of years, also could be analysed with rescaled range analysis to find signs of long-term memory. The reason why he chose these seemingly unrelated measurements is that they all have long periods of measurements going back centuries, and all were related to weather and climate in some way. Hearst didn't just study the Nile, and as a result, we know that the long-term memory effect is also valid for a whole range of phenomena hidden in time series all over the world. The discovery of long-term memory effects would inspire future scientists and perhaps prove even more revolutionary than his work on the Aswan Dam. In 1968, Benoit Mandelbrot, a French-American mathematician, synthesized the findings of Hearst and previous work into self-similar series to arrive at a phenomenon called fractional brownian motion. Instead of measuring the flows of the river, you can imagine a particle making a random walk. It can go in two directions, up or down. This might remind you of something called brownian motion. If not, you can watch this video here. But if you plot the position of the particle over time, you get a time series. The difference with our experiment is that the particle isn't equally likely to go up or down, with different points in time going variable distances up or down. It's just like a load of die. Understand wanderings of the particle, the so-called fractional brownian motion, and the furthest point that the particle reaches is the same problem as finding the most likely height of floods of the river. The long-term and short-term dependence displayed by such motion is underpinned by the Hearst index, H, which Mandelbrot named after Hearst.
Fractals, thus, with the development by Mandelbrot, came to have an algebraic expression, apart from their constructive geometric interpretation, examples of which were already known in its time. The algebraic form has significant importance because it allows one to easily generate a process which displays clustering and correlated increments, as well as to apply it under various conditions. As a result, fractional Brownian motion came to be prominently used in financial data analysis, to more reliably gauge risks relating to crises as people act in unison in times of depression, computer graphics, where it is ubiquitous in texture rendering and creating natural-looking landscapes, as well as modelling many other physical scenarios.
Back to the Nile. In 2025, Ethiopia opened its own dam, the Ethiopian Grand Renaissance Dam, which is the largest hydroelectric power plant in Africa by capacity, with over 6,000 gigawatts of installed capacity, which is enough for Ethiopia to export to other growing African countries who want a share of the benefits of the river. However, Egypt and Sudan, who for years have been regulating the flow of the river with their own dams, are critical of Ethiopia for releasing large volumes of water in short time intervals, causing flooding in the Nile Delta. Moreover, changing climates and increased water demand for expanding agricultural land change the variables that mean that calculations made in the 20th century about how to build dams no longer apply. This leads to an interesting question, and a now highly political question. who decides how much water to let through the dam? And with climate change, how countries respond to flooding through building mega infrastructure projects and managing their water, how will it affect other countries?
How will countries adapt and coordinate to make sure that everyone is equally protected from climate change and benefits from the natural resources that they have? What kind of patterns will we see in the rest of the century and into the next as man-made and natural phenomena interact on increasingly large scales?